In this video, I'll be looking at some questions taken from the motion of a body along an inclined plane. The question here says an object of mass 4 kg rests on a plane. The coefficient of static and dynamic friction are these 0.3 and 0.2. And we are told that the plane is inclined at angle theta degrees to the horizontal. Question 1 says we should find the maximum value of theta for which the object remains at rest. Okay, let me quickly show you a picture of this body at rest on a plane that is inclined at angle theta degrees to the horizontal. Now the mass of the body is given 4 kg is the mass of the body. And we can draw the free body diagram that is showing all the forces acting when this body is at rest. Number 1 is the weight of the body acting vertically downward. That is mg. Now we have the normal force. The normal force N is always acting in the direction perpendicular to the surface of the plane. Then we have the component of the weight, which is mg sin theta, that acts down the plane, parallel to the plane. Now for this body to be at rest, it means the static frictional force, because the natural thing is that this body will tend to slide down. That's the natural thing that happens to this body. The motion of the block is in this direction, meaning that frictional force will quickly come in to oppose the motion of this body. And this frictional force is called the static frictional force. So, which means if this body must remain at rest, these two forces must be balanced. That is the component of the weight acting down the plane, which tends to pull the body down, and it's being opposed by the force of friction. That is Fs, the static frictional force. Then perpendicular to the plane, the normal reaction must be balanced by the component of the weight. But when this weight is resolved, there's a component of it, mg cos theta, that acts at right angles to the plane, and it balances the normal reaction N. So for static equilibrium, we have the normal reaction equals, that is, these two forces must balance, meaning they must be equal to each other. I can call that equation 1. And the static frictional force Fs must be equal to mg sin theta. That is equation 2. Okay, I want to divide equation 2 by 1. I want to place equation 2 under this, which is mg cos theta. I bring equation 1 under and I divide both of them. That gives me that Fs over normal reaction. This cancels, this equals tan theta. Now, the ratio static frictional force for normal reaction is defined as this coefficient of static frictional force, which is given by tan theta. And static frictional force is always the maximum or limiting frictional force. It is greater than kinetic or dynamic frictional force. That's the maximum force that must be overcome before a body starts moving for the very first time. Okay, so which means in this case, this my angle theta will be maximum. Then we come back to the question. We're given that as 0.3, my coefficient of static friction. So equate that to 0.3. So that my maximum value of angle theta is tan inverse of 0.3. Okay, so I'll quickly go back to my calculator to find the tan inverse of 0.3. That gives me roughly 16.6, which is 17 degrees. So that's the maximum value of angle theta for which the block of mass must remain at rest. You can see that this angle theta does not depend on the value of the mass, whatever mass it is. For that mass to remain at rest on this surface, the angle of inclination must be equal to 17 degrees, as we have shown here. Okay. Now the next question quickly says we should calculate the acceleration of the object if it starts sliding down from rest. What is the object's acceleration if it starts sliding from rest? Now when it starts sliding from rest, in that case, we see that the resultant force on the body in the second case is given by mg sin theta minus fs equals mass times acceleration. But I need to show you something here, that the frictional force acting in this case, when this body is now sliding down, is called the kinetic frictional force, which equals mass times acceleration. So the acceleration is along the x direction. So that is what I'm going to find here. The acceleration of the object if it starts sliding from rest. Now, my Fk, which is kinetic frictional force, is given as mu k times normal reaction. A normal reaction is equal to mg cos theta. That gives me Fk equals mu k times mg cos theta. That's my frictional force, which we also called the kinetic or the dynamic frictional force. Because this time around, the body is in motion, it's already moving, and it's going to be less than static frictional force. Static frictional force comes to play when the body is just about to move. It's called the limiting frictional force, the maximum force that must be overcome before this body is set into motion or begins to slide down the plane. All right, so I have this expression as my kinetic frictional force. So I'll make substitution here so I can find the acceleration of the block down the plane. Okay, so I need to shift to somewhere here. So I have here in my whiteboard, I can call this my whiteboard. Okay, so we have mg sin theta minus mu k mg cos theta is equal to ma. So the weight, the mass of the block is 4 times 9.8 sin 17, because we are told that if it slides down at that maximum angle, okay, minus 0.2, that was giving me as the coefficient of static kinetic friction, times mass of the block 4 times 9.8 cos 17 is equal to 4a. Okay, I want you to quickly apply your calculator to solve this for me. That gives 4 times 9.8 times sin 17, that gives me 11.46 minus 0.2 multiplied by 4 multiplied by 9.8 multiplied by cos 17 gives me 7.49 equals 4a. So that 4a now equals 11.46 minus 7.49 gives me 3.96. The acceleration of the block down the plane is 3.96 divided by 4. That gives me an answer 0.99, which is approximately 1 meter per second squared. Okay, that's the acceleration of the block down the plane using the ideas of the resultant force that acts on the body from Newton's second law is the difference between these two forces. Since the motion of the block is this direction, it means that mg sin theta will be greater than fs for the body to accelerate in this direction. And I said that in this case, the frictional force is no more static. It is now kinetic since the body is already in motion. Okay. Now we are told the last question that suppose this body starts from rest, how long does it take to move a distance of 3 meters? If you start from rest, means initial speed is 0. Now we apply the ideas of kinematics here to solve this problem. We are going from kinetics to kinematics. The acceleration we've calculated as roughly 1 meter per second squared. And now we are looking for the time taken to cover a distance of 3 meters. We can recall the second equation of motion. Distance is this plus half at squared. Okay, since it starts from rest, my ut is 0. That gives me, the equation simplifies to this. That's 3 meters equals 1 times this times. So that gives me 0.5 t squared. And then t squared divided both sides by 0.5 gives me 6. That is time t is the square root of 6. That gives the time taken to move a distance of 3 meters, 2.4 seconds. So that's what it takes to move that distance of 4 meters. Okay. All right, quickly, let's see another question. For this question, we have a block of mass on an inclined plane that is inclined at angle 30 degrees to the horizontal. And the mass of the block is 50 kg. And we have a frictional force. Let me include that. Opposing motion. Okay, let's say this block is already moving. We have to find the tension in the string, because by means of this string, the block is pulled up the plane. This is the direction of motion of the block of mass. So how do we calculate the tension in the string? Case 1, when the block moves at a constant speed, or the block accelerates at the rate of 1.5 meters per second squared, or the block decelerates at 2 meters per second squared. Now let's write an equation for the resultant force acting along the direction of motion, that is along the inclined plane, as some of the forces along the x direction. Okay, we can give the tension positive because it acts in this direction. Recall that I need to include one more force, and that is the component of the weight. The weight of the body is mg. If we resolve that along the plane, it is mg sine theta. Of course, you recall there's another force I need to include. That is normal force, normal reaction. Okay, so I have that. Resolving along the plane, tension minus mg sine theta minus the frictional force 160. Of course, that's going to be the kinetic frictional force equals mass times acceleration according to Newton's second law of motion. This expression gives the resultant force that acts on the body of mass m. Okay, so the forces minus this minus mg sine theta and minus 160 are both acting towards the negative x-axis, so we give them the negative sign. Okay, now if the block moves with a constant speed, it means the acceleration of the block is 0. That this equation reduces to t minus mg sine theta minus the frictional force Fk, because this time around is kinetic frictional force that is given, equals 0. Okay, so the tension in the string is just the sum of mg sine theta minus the kinetic frictional force, which was given in the question. That gives me this equals the mass of the block is 50 times 9.8 times sine 30 minus 1. Sorry, this is plus 160. Okay, yes, that's plus, not negative, please. So that gives me 50 multiplied by 9.8 times sine 30 will give me 245 plus 160. The tension in the string is equal to 45 Newton. Okay, that's the tension when the block moves with a constant speed. Now, what is the tension in the string? The second question. If the block accelerates at 1.5 meters per second squared. So the same equation for resultant force T minus mg sine theta minus Fk equals ma. Okay. Now this is equal to mg sine theta plus Fr plus ma. Okay, so that gives me 50 times 9.8 times sine 30 plus Fr, which is that's my Fk, which is 160, plus mass times acceleration, which is 50 times 1.5. Okay, the tension in the string when the block accelerates, I have the 50 multiplied by 9.8 multiplied by sine 30, which is 0.5. Okay, that gives me 245. We've done that before. Plus 160 plus 50 times 1.5. That gives me 75. So when I add 405, which is sum of these two, to 75, that gives me 480 Newton. So that gives the tension in the string. You can recall that the tension in the string in this case is greater than the tension in the string when the block was moving with a constant speed. The last question says when the block decelerates, so you see the same equation. Resultant force is tension minus mg sine theta minus this equals m times a. Now this time around, since the block decelerates, I'm going to replace my acceleration with negative, because negative acceleration means deceleration. That gives me this tension in the string equals minus ma plus mg sine theta plus the kinetic frictional force. So the tension in the string gives me minus 50 times 2 plus 50 times 9.8 times sine 30 plus 160. Okay, so in this case, t equals minus 100 plus 245. That's if you take the product of this and this. So that my tension in the string gives me 405 minus 100. That gives me 305 Newton. So the tension is least when the block begins to decelerate.